strong Lewis acid catalyst, and they have very good property, and they can interact with amine molecules. So like this way, and they can generate frustrated Lewis acid base pairs. And these frustrated Lewis acid base pairs are very active, and they can react with carbon dioxide molecule easily, and can we can do other reduction reaction of carbon dioxide. So in point of view, I have used this boron. It's a very famous catalyst for the fixation of carbon dioxide, and dimethylamine boron as a very green and solid material for the generation of hydrogen instead of hydrogen gas, and to synthesize of various formamides. We have synthesized a lot of formamides, but I haven't represented here, and some cyclized compounds like benzimidazole and their derivative as a very important scaffold for the pharmaceutical and drugs to synthesize important molecules. Then next scheme we have synthesized. I have worked on the synthesis of because I was looking, because as I have discussed, the carbon dioxide is highly not reactive; it's highly neutral. So we need to find some very strong catalyst, like a very strong nucleophilic or electrophilic. So we have decided to synthesize some super base ionic liquid like a DAPCO. So we have synthesized the DAPCO. In addition to that, we need to some catalyst to activate starting material like epoxide and other things. We need some hydrogen bonded catalyst. So we have synthesized this type of 9 ionic liquids, which are also the supported on solid material and homogeneous case. And we have used this catalyst for this carbon dioxide fixation for 3 types of reaction: the normal epoxide to the cyclic carbonate, then the transesterification of synthesized cyclic carbonate to the dimethyl ether as a very important fuel, and diol as a another sustainable chemicals, and the synthesis of quinazolone dione, another important pharmaceutical molecule, by using simple carbon dioxide and synthesized catalyst, which is. So these are some process of synthesis of the ionic liquid. They are basic and acid base bifunctional. So we can say they are bifunctional because they have moderate acid and very good basic characters. So they can act as very strong base for all this conversion. And these are the characterization they have when we have used the solid supported catalyst, and they have I found very nice morphology. And then due to this solid type of structures, and they are very easy to recycle from reaction media, and plus they have very high stability near about 350 degrees Celsius, and which is a very good sign for use them as a catalyst. So we have synthesized various cyclic carbonates also, and then we have fixed the CO2 molecule, and then reviewer said just try some reaction with carbon disulfide, which have a similar activity. So we have also reacted this compound epoxide with carbon disulfide, and we have synthesized various sulfur molecules, and including the quinazolone and the means the thioquinone type of molecules, and again for the synthesis of dimethyl and other diol functional group. So that is we have done with this catalyst. Then again another type of ionic liquid which containing biodegradable and bifunctional. I was looking for the bifunctional, and which should have to be like a biodegradable in nature, because after synthesis of the ionic liquid, it's very difficult to them to biodegrade because they are chemically very stable. So I'm looking for some ionic liquid which can be synthesized like this one. So I have synthesized some ionic liquids which are bifunctional in nature from the choline chloride as another biodegradable material, and which we have reacted with the various amino acid group, and this amino acid and this choline chloride form choline amino acid ionic liquids, and they are very active for this cyclic carbonate, and this synthesis reaction we have characterized, and with stability by TG analysis they showed very high stability. And then we also checked the recyclability of the synthesized ionic liquids. So we found that they are very recyclable in nature. And then we studied some spectroscopic with spectroscopic characterization, and we found that the formation of the presence of amine functional group which can absorb the carbon dioxide molecule and which help for the catalysis or the activation of this reaction. So we have, and based on this one, we have developed a reaction mechanism where the epoxide and the other co-catalyst help to form the hydrogen bonding reaction and then nucleophilic addition. And then the available carbon dioxide molecule is activated by the presence of amine molecule on the amino acid, and this amino acid then further helps for the cyclization of this epoxide molecule to this synthesis the cyclic carbonate. So we have did this some reaction kinetics, and we found that the time and everything we have did other things. Then I have worked on some heterogeneous catalysis things. So here we have synthesized some MCM41 based material which having both the functionality, as I am saying, because I was looking for the acid and base as a bifunctional catalyst. So we have synthesized the mesoporous silica which have tubular form, and inside the tubular form we have loaded the amine functional group and zirconium oxide as a Lewis acid, and amine as a Lewis base for the activation of the carbon dioxide and epoxide. And we successfully loaded this catalyst, and then we use this for the scalable synthesis of cyclic carbonate by using this bifunctional catalyst. And we have loaded this with different like a to 3.2% amine functional group, like 16% and 12% to maintain the bifunctional nature. And we found that the 16% of amine functional group loaded this silica with zirconia have a high activity, and we have characterized this material using X-ray diffraction study and ammonia TPD and CO2 TPD to check the acid-base nature of the catalyst, and they found that it have an acid and base bifunctional nature, and we use this for the various reaction. And again similar type of reaction mechanism which show the zirconium oxide acts as a Lewis acid and the amine functional group as a Lewis base, and it will help to synthesize this product. And another type of mesoporous silica we have used, because all the silica we have synthesized, generally the people are synthesizing having the tubular structure. When we load any functional group like amine functional group or any other nanoparticles for design of other catalysts, generally they blocks the pore. So we are looking for something different silica which having the spherical morphology